Okay, this is going to be a quick screencast because it's only one type of problem we're going to look at, and that's exponential decay. And we usually use it when we talk about the half-life of radioactive substances. And so the half-life of a radioactive substance is the time required for it to lose half of its mass. Let's say I've got a substance that starts out with 128 grams and it has a half-life of 10 days. So let's say that we're starting with 128. After 10 days, we've lost half of it, so we're down to 64. 10 more days, we've lost half, we're down to 32. 10 more days, we're down to 16, and so on and so on. So remember that you're not losing the same amount of mass, you're losing the same percentage of mass. All right, here are the half-lives of some typical isotopes. Carbon-14 is very famous because we use it to date archaeological finds, and they go all the way down to polonium-214, which only has a half-life of 1/10,000th of a second. Okay, here's how we would use it using this formula. The percent amount of a radioactive substance after T years is 0.5 raised to the T over H. T is the time and H is the half-life. And here's an example. What percent of carbon-14 will bone have after 10,000 years? So P of 10,000 will equal 0.5 raised to the 10,000 over 5,730. We'll use our calculator to evaluate this. So I'm going to go 0.5 raised to the 10,000 divided by 5,730, and I get 0.298, which is close enough to 30%. So after 10,000 years, it's lost 70% of its carbon-14. And finally, let's turn it around. Let's say we know the percentage and we'd like to know how old the bone is. So 0.75 equals 0.5 to the T over 5,730. Since the unknown quantity is in the exponent, we'll use logarithms to solve this. And that allows me to bring the exponent around front. And solving for T, I'm going to multiply by 5,730 and divide by the natural log of 0.5. That should tell us how old a bone is that has 75% of its carbon-14. Okay, let's get our calculator up here again. And I'm going to go 5,730 times the natural log of 0.75. Whoop, left off the point. 0.75. Well, left off the 7. There we go. Divided by the natural log of 0.5. And we get 2,378 years old. Okay, so those are really the only kinds of problems you're going to see involving exponential decay.